In 1964, Israel built a pipeline to pump water across hundreds of kilometers of desert. Over 60 years, the country pumped billions of cubic meters into it. When scientists finally began measuring the consequences, the numbers turned out to be impossible. That changed the entire plan. If water had already transformed the desert so profoundly, what would happen if it were sent back? Israel then launched a comprehensive overhaul of the country's entire water system. But while engineers were reversing the pipeline, scientists in the desert were recording something year after year that didn't fit any model. The south of the Negev receives rain less often than the Sahara. Just 25 millimeters a year, less than evaporates on a single hot day. Summer temperatures reach 47 degrees. Plants don't grow here, they survive. And yet even for the Negev, 1998 was extraordinary. The drought was the worst in 900 years. It was drying out not just the desert, the Kinneret, Israel's main freshwater reservoir, was approaching its black line every day, the threshold below which the lake might never recover. The level of the Kinneret began to be announced on the evening news, alongside the exchange rate and the weather forecast. The country watched the number and understood, if nothing changed, there would be no water. People didn't realize we were in an emergency, Firas Talhami, director of the Kinneret division of the Water Authority, would later say. But the 1998 crisis didn't come from nowhere. Israel had been building the pipeline from the Kinneret southward since 1964. 130 kilometers of pipes, tunnels, and reservoirs, 72,000 cubic meters per hour. At the opening ceremony, Ben-Gurion stood beside the pipe and spoke about the future. 80% of the water went straight to the fields, but the system depended on a single source, the Kinneret alone. No rainy winter in the north meant no water in the south. There was no buffer. Every year, extraction exceeded natural replenishment. The debt accumulated slowly. 1998 presented the bill. The country began looking for a way out. The first proposal was strict consumption limits. Farmers had their water quotas cut. Cities had their tariffs raised. But restrictions don't create water, they only slow its disappearance. It became clear that a new source was needed, one that didn't depend on rainfall on the Golan Heights. But while the country was building pipelines and counting cubic meters, one engineer in that same Negev was thinking about something else. How much of the water actually reaches the root? Simcha Blas noticed it by accident. A farmer showed him a tree that was growing noticeably larger than its neighbors without any additional irrigation. Underground, they found a hole in a pipe. A small trickle of water had been seeping into the soil directly at the root every day. The tree was drinking by drops and growing better than those being flooded. Blas spent several years turning that observation into a technology, a tube, a valve, an emitter that releases water drop by drop directly to the root. No evaporation, no runoff. On August 10, 1965, he signed an agreement with Kibbutz Hatzerim in the Negev and founded Netafim, the world's first drip irrigation company. In January 1966, the first drippers came off a small factory in the desert. Today, Netafim tubing runs beneath vineyards in Napa, cotton fields in China, and greenhouses in the Netherlands. But at the time, it was just a hole in a pipe that one engineer decided not to plug. Drip irrigation solved the question of efficiency. But another problem remained, and it was more fundamental. The Kinneret gave what it gave. Rain fell when it fell. The system could be perfectly economical and still remain dependent on the sky. Israel understood. The only way to break that dependence was to create a source that didn't depend on the climate at all. Not store water better, not distribute it more efficiently, but produce it from scratch, at an industrial scale nobody had achieved before. The answer was found on the Mediterranean coast. Seawater forced under pressure through membranes with microscopic pores. The salt is held back, and the water passes through. The technology had been known since the 1960s, but the scale Israel wanted had never been attempted. October 2013. 15 kilometers from Tel Aviv on the Mediterranean shore, a plant opened that was doing the impossible. Taking water that kills plants and turning it into water that feeds them. 624,000 cubic meters per day, the largest facility of its kind in the world. But the decision that led there was a BET, not a calculation. Standard plants used horizontal pressure vessels with 8 to 12-inch membranes. The IDE engineers chose 16-inch oriented vertically. More membranes per unit area, lower pressure losses. On paper, compelling. But nobody in the world had built anything of that scale with that configuration. Each of thousands of modules had to operate in synchrony. A failure in one sector could cascade and shut down neighboring ones. The contractors had no experience with that density of connections across 10 hectares of coastline. The plant opened in October. It didn't reach full capacity until late November after final load testing. But when it did, everything changed. The cost per cubic meter fell to 58 cents, a third cheaper than in the 1990s, and for the first time, Israel was producing more fresh water than it consumed. The surplus flowed back into the Kinneret. The same lake that had nearly been killed by over-extraction in 1998 was now being replenished with water from the sea. A system that had been taking for decades began giving back. Today, more than 80% of Israel's drinking water is desalinated. The country produces 20% more fresh water than it consumes. 5 plants on the coast, 12,000 kilometers of pipe, network losses below 3% compared to an OECD average of 15%. But water is only part of what happened in the Negev. The other part began earlier and turned out to be even more unexpected. That same year the pipeline opened, Yosef Weitz, director of the forestry department of the Jewish National Fund, was looking at a map and pointing at a limestone plateau on the edge of the Negev. Here, he said, there was nothing there resembling a forest. Rainfall, 285 millimeters per year. Summer heat, 40 degrees. Soil, a thin layer over chalk and limestone in places reaching a meter deep. Potential evaporation, 1,600 millimeters, meaning the land wanted to pull from the air 5 times more moisture than it received from the sky. Weitz wanted to stop the sand that was creeping northward. People were sent in with Aleppo pine seedlings. It isn't fussy. It grows in any soil quickly, without much attention. The British Mandate administration had been planting it here since the 1920s. The JNF used it in half its forestry projects. The choice was practical, not poetic. The seedlings were carried up to the plateau. Holes were dug in the rocky ground, and they were planted without irrigation and without fertilizer. Nobody knew for certain how many would survive, and some died in the first dry summer. But some held on. 10 years later, the plateau had a young forest. 20 years later, the sand had actually stopped. 60 years later, 4 million trees across 28 square kilometers, the largest artificial forest in Israel. The task had been accomplished, but those who planted in 1964 were thinking about sand, not about what the forest does to the AIR above it. That question came later, and the answer didn't fit any plan. The year 2000. Dan Yatir, an ecophysiologist at the Weizmann Institute, installs a measurement tower in Yatir with 300 sensors and launches one of the longest continuous experiments in his field. 14 years of hourly measurements in a forest where no scientific instrument had previously survived more than one season. The forest had already survived. Now, Yatir wanted to know what it was doing to the sky above it. A technical problem arose immediately. Sensors calibrated for temperate climates failed under the sand and temperatures, ranging from -5 to +40 degrees Celsius. Eil Rotenberg, a research scientist in the lab, drove to the forest after every storm to clear filters, replace components, and climb a tower that swayed in the wind. The first substantial results came in 2010, and they were immediately puzzling. Yatir was warming the climate, not cooling it. The dark pine canopy was absorbing more solar radiation than the pale stone around it and returning that heat to the atmosphere. Rotenberg calculated that for the cooling effect of carbon absorption to outweigh the warming effect of the dark canopy, the forest would have to stand for more than 200 years. Yatir put the question directly: if the forest warms things up, why plant it? A doctoral student began looking for the answer, Rafat Kubaja, who crossed a checkpoint every day to get to work. He began measurements at Yatir in 2014 with a spectrometer that detects carbonyl sulfide molecules, a gas that plants absorb and sink with carbon dioxide during photosynthesis. This allows direct observation of what the trees are doing in real time, independently of any other sensors. The first thing that puzzled Kubaja was the August data. 5 months without rain, and the trees were still photosynthesizing. Not at full capacity, but enough that the numbers had no explanation. Kubaha searched for the moisture source. It turned out that at night, as temperatures drop, the Aleppo pine absorbs water from the air through its needles and bark. Not from the soil, from the atmosphere. It was enough to sustain photosynthesis through the hottest months. The second puzzle, where does the absorbed carbon go? In temperate forests, it settles into the trees and returns to the atmosphere relatively quickly through soil microbes. In Yatir, more than 70% went not into the trunks but into the ground, and dry soil breaks down organic matter slowly. Carbon stays there for an average of 59 years, compared to 18 years in temperate zone forests. The result? Over the period 2001 to 2016, the forest accumulated 145 grams of carbon per square meter per year. In wet years, up to 3.5 tons per hectare. The global average for forests is 2.6 tons. A forest on the edge of survival was sequestering carbon more efficiently than most forests on the planet, and holding it in the ground 3 times longer. Rotenberg revisited his calculations. Accounting for underground accumulation, the balance shifted toward cooling far sooner than the first model had shown. Yatir is the driest and warmest forest in the world that I know of, Kubaja would later say, by then at the University of Arizona. It shows what conditions will look like in the future. Yatir applied the data to a global model. The conclusion: semi-arid zones cover 1/5 of the planet's land surface. If suitable areas in Africa and Australia were planted with trees, they could absorb roughly 10% of annual emissions from fossil fuel combustion, more efficiently than the same investment in plantings in humid zones. The forest planted to stop sand had ended up at the center of global climate calculations. Nobody planned for that. But that is how the Negev works. Every decision here produces consequences nobody anticipated. And while scientists were counting carbon above the canopy, below it, and in the air, the water in the desert continued its own cycle. 87% of Israel's wastewater is treated for irrigation. The second-ranked country in the world, Spain, treats 20%. The United States, less than 10. 67 treatment stations. The main one, Shafdan near Tel Aviv, cleans 400 million cubic meters per year and sends it by pipeline to the Negev, where it irrigates 60% of the fields. 40% of Israel's agricultural output comes from the Negev. Cotton, dates, sunflowers, olives, wheat, citrus. Cotton, one of the most water-intensive crops on the planet, grows in the desert through drip irrigation. The plant receives 95% of the water delivered, compared to 50 to 60% with surface irrigation. Southwest of Beersheba stands the Ashalim Solar Power Station, a tower 260 meters tall, 50,600 heliostats, 320 gigawatt-hours per year, plus parabolic troughs and photovoltaics. Together, 120,000 households. A desert that for decades produced nothing is now generating water, food, and energy simultaneously. But there is one more fact that rarely makes it into the statistics. Drip irrigation covers 75% of Israel's fields. Across the rest of the world, 5%. This difference is not about technology. The technology is available to everyone. The difference is that in Israel, a farmer in the Negev pays enough for water that there is no choice, either drip irrigation or bankruptcy. Scarcity made efficiency mandatory. And that is why cotton grows in a desert that receives 25 millimeters of rain a year. But there is something else that grows in the Negev, and it is even less expected than cotton. In 1979, during drilling in the Arava Valley in the eastern Negev, water was found at a depth of 700 meters. It was unfit for drinking, brackish and hot, around 37 degrees Celsius, heated by geothermal forces deep in the earth. For wheat, poison. For drip irrigation, useless. For any standard application, a dead end. But scientists looked at this water differently. They studied warm rivers in northern Australia and brackish lakes in East Africa and found the ideal candidate, barramundi, a tropical fish that thrives in exactly this kind of warm, slightly saline water. In 1992, Kibbutz Mashabasade built a 3-hectare reservoir in a series of covered tanks. The geothermal water from the fish ponds flows after use onto olive trees and melons. a closed loop in which the same water feeds both the fish and the field. Today, the Aquatech plant in the southern Negev raises 2,000 tons of barramundi per year, from water considered unsuitable for any other purpose. Water found by accident during drilling turned out to be perfect for exactly what nobody was looking for when they drilled. Shafdan, the main wastewater treatment plant near Tel Aviv, receives 470,000 cubic meters of sewage daily. Water that millions of people used at home, in restaurants, in businesses. Shafdan runs it through biological reactors, cleans it, and pumps it south to the Negev. 60% of the agricultural water in the desert is exactly this water, treated, cleaned, returned. A farmer in the Negev irrigates cotton with water that was in someone's shower in Tel Aviv that morning. The KKLJNF has built 230 storage reservoirs for treated water across the country. Every year, they add more than 260 million cubic meters to the country's water balance. Every drop in Israel lives several lives. This is the system that Ben-Gurion saw in broad outline back in the 1950s, but couldn't have imagined in detail. Desalinated seawater, treated sewage, drip tubing under every cotton plant, all of it has closed into a single loop where every cubic meter passes through several hands before it disappears. The Negev, which was supposed to remain a desert, feeds the country, and it is here, at the boundary between what worked and what went wrong, that there is a question nobody likes to ask out loud. But let's stop here. 5 to 10% of Yatir has died back over the past decade. A series of droughts, and the young trees are not regenerating. Goats and sheep destroy the seedlings before they can take hold. The climate is becoming harsher in exactly the place where the forest already exists at the edge of survival. And there is another problem, one that doesn't come up in presentations. Before Yatir, this landscape was home to lizards, insects, and birds adapted to open rocky terrain. The pine canopy displaced those ecosystems. The heavy machinery used during planting destroyed the fragile soil crust of lichens and mosses that sustains the chain from insects to birds of prey. Yatir stops sand, sequesters carbon, and destroys what was there before it. 3 things, and all 3 are true. Science does not yet have an answer to which of them matters most. The KKLJNF has already announced a plan, planting new seedlings throughout Yatir over the coming years. But this time, not as in 1964. Back then, Aleppo pines were brought in and planted without questions. Now, a team of foresters assesses each dead section individually. What slope, what soil, how much sun, and decides, plant pines again, or try something else. Oak, pistachio, or don't plant at all and let the desert come back. On one section, walnuts grew for 30 years. They didn't survive. Now there is bare rock and the same silence that existed before 1964. Yatir is not nature restoring itself. It is a decision that has to be made again every year. And for the first time in 60 years, the answer is not obvious. The winter of 2024 to 2025 was the driest in the Kinneret Basin since records began, over 100 years of measurement. The lake level dropped 172 centimeters in a single year. In February and March, the months when the Kinneret traditionally rises, daily declines were recorded, for the first time in history. In October 2025, Israel did something it had never done before. It launched the pipeline in reverse. Desalinated water from the Mediterranean now flows back into the Kinneret. The same pipeline that had been pushing water from the lake southward since 1964 now delivers water into the lake from the west. Last winter was the driest in 100 years, and the Kinneret has dropped to a level we are not prepared to cross, said Water Authority Director Yehezkel Lifshitz. The system built as a response to scarcity is now saving the reservoir it was built to serve. This was not anyone's plan. It is where 70 years of trial, error, and crisis led. Sorik 2, launched in 2025, produces 200 million cubic meters per year, the world's first steam-driven desalination plant. Israel, which as recently as 2004 was entirely dependent on rainfall, now exports desalination technology to dozens of countries. By 2050, 40% of the world's population will be living in regions with chronic freshwater shortages. most of them in the same semi-arid zones where Yatir and Kubaja measured carbon between pine crowns and the Negev sky. Yatir still stands. The sensors are still recording. And the question Yatir posed in 2000, what happens between a tree and the atmosphere on the driest August night, still has no complete answer.